Okay, so let's get started. As you can see my screen, right? No problems.
Yes, sir.
Okay, so today we're going to talk about what is called transfer function. Uh, some of you may have already heard about it, but whether you know what exactly it is not very certain. So therefore, we'll look at the basics and figure it out. What is it and why we need to use what is called transfer function. Okay. Now, I always relate theories into physics, right? Uh, that is absolutely necessary if you want to be a master of almost anything, but in particular, this area, when you deal with systems, right? Controls, etc. So let's look at this shock absorber thing because now you are familiar with this system. Okay. I think you know everything, the damper, the spring, the motion, the differential equation here, right? So you derived it and you know what these things are, okay? So there's absolutely nothing that you don't know here, right? And also on the right hand side, the free body diagram, right? So without any physical devices, right, that cause the motion, we only draw the arrows, right, with their descriptors for forces, right? So there are three forces acting on the mass, and because of any imbalance force, the mass has to accelerate. So then we write down the equations and derive the system equation. So this is it. Then what we did was we used the Laplace transformation, right? Because we don't want to deal with differential equation um, explicitly, right? When I say use Laplace transform, it doesn't mean that you don't do differential equations, right? No, you do. But it's like cover up. You do it in a different way, okay, using Laplace. So then when you put this equation, right, into Laplace domain, right, you get this one. Nothing new here. We have done all these things in previous weeks. And then we figured out the two components for YS. YS is the response, right? Equation 3.52, recurring equation 3.52. Now, this is very familiar to you. Now, we open a new discussion from here. We have been in this situation earlier, and we continued from this point 3.52 in one direction. I think you are pretty confident about what we did. Now we go back to that same junction, right? And we continue in a different direction. Okay. So there what we say is this: neglect the initial condition response. This one. Why? I think I described this to some extent earlier. I want to reiterate because a number of reasons. One, the initial condition causes only very short lasting effect in the response. Short lasting. So whatever that you see in the response, let's say if it is a motion, any motion because of the initial conditions is only temporary. It doesn't last long. So if you can just let it be there for a small period of time without doing anything to counter, right? And if you know that it's still stable, right, uh, then you can simply neglect it. Why you want to make things complicated? For something which is surely going to go away, right, you better neglect it, which means whatever relationship you have in the mathematical expression is not accurate in the early initial few milliseconds or couple of seconds, right? There can be differences of from the actual observation and the simulation expectation, but this is only short lasting. That is one thing, one justification to neglect that. Second, you don't have any control over this, right? Typically, we can say that you can have some sort of control artificially, but directly, you don't have any authentic control over this initial condition response, because it is coming from the stored energy of the plant, accumulated energy of what has been happening up to that point in the past. Okay, and some systems have that accumulated energy, some systems don't, and it is completely independent of what you do to the plant. It's totally independent of the input. There you can see this is the input, this is our presence, right? What we do to the system, and this is completely different term in the response. So therefore, we don't like to have anything that is not under control. Okay, it only makes things complicated. So that is the second reason to neglect that one. So what we really want to know, right, or to do from this point onwards is that what is the response to my input? So that is what I want to know. Input output relationship. Okay, and if the input is input has some component not coming from, sorry, if the response has a component which is not coming from the input, I'm helpless, right? So I want the response to be completely related to the input 100%, right? But unfortunately it's not the case, and sometimes there are initial condition based components in the response. So now we give this name transfer function, meaning transferring something from input to the output. If you look at that relationship, of course, you don't have to deal with the initial condition response, right? So once you drop that part, what remains is on the left hand side ys, on the right hand side this very simple expression of fs. Fs is the input. So you generate this equation, right? Ys is equal to eta over s square plus 2 sigma s plus rho times fs, and we give this name transfer function. Transfer function, transferring from input to the output or to the response, right? Then once you get this fs to the left hand side, it is ys over fs. This is coming very like rational polynomial format, ys over fs. On the right hand side, eta over s square plus 2 sigma s plus rho. Okay, so now this is the lasting relationship between input or the reference and the output or the response. Reference and response relationship, right? So we draw it as a one block here, eta over s square plus 2 sigma s plus rho, and this input arrow and the response ys. So that is how the transfer function word and this transfer function comes to light. Okay. Now let's take another example. we have done two examples, and this is bit complicated, right? But it's very typical example. Every control system undergrad has to go through, right? So what you see over here is a motor gear system, right? Connected to a arm, a robot arm, and the motor is actually actuated by this control circuit, right? And eventually there's a voltage source here. So when you apply this voltage, there's a current flowing through the circuit, through the motor. The motor gets a voltage and a current through it, and it turns. Then this motion is transferred to the robot arm through the gear, so the robot arm also moves. So eventually the response is theta, the angle of the robot arm, and the input is this voltage. Okay, so we are trying to analyze this electromechanical system and try to figure out the transfer function between the theta, the output or the response, and Vt, which is input or the reference. Okay, again, there's no control here. We want to see if we apply this voltage, what's going to happen here. So can I ask some questions? Before we do anything, can you turn on your mics and tell me, if I turn on this voltage, right, what do you expect to see from the other side? What is your expected observation?
Shaft will rotate.
Say it again.
Shaft will rotate.
Rotate. When you say rotate, can you describe it a little bit? Can you describe the motion that you expect?
So in the when the motor shaft rotate with the gear wheel over there, the
Yeah.
limb will move left to right.
Yeah, but I want you to describe it further. When you say rotate, whether it rotates continuously at the same speed or whether speed
It rotate like
increases,
steps, step by
whether
step.
yeah. So
We
tell
control.
something more about it. Go on.
It will not rotate continuously, sir. It will rotate with a step as a stepper motor or something.
So you mean it will move in steps?
Yes, sir. According to because it is arm or something, robot arm or something.
So it will move, say, whatever number of degrees and stop.
Yes.
Okay, that is one expectation. Anything else?
Angular speed will be 0, then gradually increase up to some certain value, then it will be remaining at the certain value. Angular speed, angular velocity.
Right, so let's say 50, 60 degrees, it will be there. It will initially start from 0, right? Build up and then stop at some point, right?
No, angular velocity, it will come to some angular velocity, then it will rotate the same angular velocity.
It will keep on rotating with the same speed.
Yes.
Okay, that is one answer. Anything else? Anything else? Okay, so let's go ahead and analyze. Let's go ahead and analyze. Right. So there are two points here. First one, before you do anything, you need to look at what you have, right? And get some rational expectation, right? Some rational expectation of what it should do, right? and that will help you to develop your mathematics modeling. Okay, so that is extremely important, but do not stick to any of these initial expectations too much, only to some extent, right? Otherwise you will write down equations to achieve what you expect. That is also not correct, right? So you have to draw a line. Okay, the first thing, we get the electrical system, this system, right? We write down the equations for that, right? So then voltage is on the left hand side, right? Vt is equal to, now there's a current drawing like this, so there's a voltage drop across the resistor, voltage across this inductor, because there's an inductance in the circuit. And also, as you know, when a motor runs, the motor develops opposing voltage to the input voltage. Okay, this is the input voltage, this is the opposing voltage. So as the motor speeds up, this opposing voltage also speeds up, raise up, right? So then when you try to increase the speed of the motor, it doesn't give you the same quick speed increase, because as you improve the voltage, right, as the motor speeds up, it will build this higher and higher and higher opposing voltage. So therefore it will be increasingly difficult to further speed up the motor, because the remaining voltage between these two is diminishing. Okay, that is why these kind of typical motors, when you give a voltage, attain some speed and then not beyond that. Now the voltage across the resistor is IR, plus voltage across the inductor is L di by dt. So I want you to get back to your basics if you have already forgotten, right? What is the equation for a resistor? Of course, IR. What is the equation for an inductor? What is the equation for a capacitor? These are very basic stuff. I need to remember all these things, right? So for a inductor, it is L di by dt. Voltage drop across an inductor which is carrying current I, right? The voltage is L di by dt plus Vb, that is the back electromotive force, EMF, of the terminals of the motor. Now, from the motor side, we know this, that the back EMF of a motor is some constant times theta dot m. Theta dot m, this dot has to be here, right? Theta dot m, that is the speed of the motor, right? You calculate the speed of the motor, right, and multiply by kb. Then you get, okay, how much back EMF is there. So that is the electrical system equation. And then what you do is you substitute for VB from the motor, that is kb theta dot m, right? And then of course you can use Laplace for simplification. So Vt becomes Vs, I becomes Is, right? Di by dt becomes what? SIS, right? And you can eliminate the initial conditions because we are not interested anymore about initial conditions, plus kb theta dot m. So it also becomes S theta ms, right? Laplace. When you have a differentiation in the time domain, the Laplace domain, it is S times Is, S times theta ms, and also initial conditions. But here, because we decided not to consider initial conditions here, we drop them. And after that, you can take Is, which is a common term here, and also kbs theta m s 3.69. So write down this equation somewhere, right? The first equation for of this example is Vs is equal to R plus Ls Is plus KBs theta Ms. So we have figured out a relationship between the voltage, right, and the current of the circuit and theta M, motor angle. So now you can think that this is not what we want. We want theta, this angle, and this voltage, right? So this is something in between. We have Is, we have theta Ms. Now, I can also see that theta M, which is the motor angle, and the load angle, this theta, they are related. So I don't have any problem with this one, because theta M is actually n times theta. This is a reduction gear, as you know. When this shaft turns about 100 turns, this turns 1. Okay, it's about 100 to 1, or 60 to 1, or 50 to 1 kind of ratio. So therefore, if I know theta M, I know theta as well. So that I can adjust. But Is is something that I don't want to be in the final equations, right? So I want to get rid of Is, current. Fine, let's move on. These are some of the terms in this example. Vt, we call it armature voltage. Jm, motor inertia, the inertia of the motor. N gear ratio. Armature inductance, right? Bm, motor damping coefficient, right? JL, inertia of the arm. KB, motor back EMF constant, right? How many volts it generates as it turns in 1 radians per second. So when you have 2 radians per second, 3, 4, 5, 6, you produce that many volts, right? As back EMF. Theta M, motor shaft position, theta arm position. Then the current through the circuit, armature current. Then K tau, torque constant. For every motor, there's this torque constant, which means if you drive 1 amp through the motor, it generates this amount of newtons as torque, a Newton meter rather. Then this is the load shaft torque, right? The torque on the load shaft, right? Not motor, because there's a gear, right? Then VB, back electromotive force, there is a voltage, opposing voltage from the motor. Then we have motor shaft speed, theta dot M, and we are getting a noise. Somebody's keeping the mic on. Please check your microphones. R, armature resistance, motor shaft torque, viscous damping constant of the arm. So now when you look at the moving parts here, they have friction, which is damping basically. So motor has some friction, and also load has some friction. So load is after the gear. So load is moving slowly. Motor is moving fast. Okay, because of the gear, some of this inertia do not transfer to the motor side in the same scale, right? We're going to look at that. There's a scale adjustment there every time when you go past a gear. So these are some of the fundamental equations in mechanics. If you have a gear, right, motor is connected to a load through this gear, right? If you see from the motor side, what is the total inertia that you see? If the motor is running freely, you see Jm, motor inertia. Okay, if the motor is running slowly. But if the motor is coupled with load, right, through a gear, and if the load inertia is JL, and if the gear, which is reduction gear, 1000 to maybe 100 to 1, 50 to 1, 150 to 1, that kind of reduction, speed reduction gear, and let's call that gear ratio is n to 1, right? Then the entire inertia on the load, as you see it from the motor side, would be JL over N square. That you have to remember, inertia divided by N square. If the gear is a reduction gear. Similarly, if you look at the friction, there is some friction in the load side. When it transfers to the motor side, which means when you see it from the motor, right, not only the inertia, the friction of the motor, because it has bearings, etc. When you try to turn, there is a friction. And now you have more friction because there's a load, right? So that load is also now is visible when you see it from the motor side. So how much of that is going to be seen from the motor side? Again, the damping of the load BL divided by N square. Again, if it is a reduction gear. Now that is done, both equivalent inertia and equivalent damping. Now we can write this equation, torque equation, right, to the motor. Motor generates a torque, right? When there's a current flowing through the motor, it generates a torque. So this torque is used to drive the motor, right, and to overcome friction. So the first part here is theta dot m BEQ, the total inertia that it has to overcome, BEQ theta dot m, right? So depending on the speed it rotates times BEQ is the total torque required to maintain that speed. And also the initial torque, JEQ, equivalent inertia times theta double dot m. If there's any acceleration, right? If there's an acceleration, in order to exercise this acceleration, you need to generate this much of torque. Okay, so this torque is used to maintain speed and accelerate further. However, we know from motor side, the torque that a motor generates is K tau times IT. K tau times IT, right? If you know the current going through a motor, multiply with that constant, you get the total torque. So because of that torque, when you put it into this equation, right, you can calculate the acceleration. Motor accelerates initially, okay? So as the motor accelerates, it generates the speed. So therefore, you now need to spare some part of the torque in here, okay? So then you are remaining with less for the acceleration part. So therefore, the acceleration will reduce. You don't have the same high acceleration that you had initially, right? When there was no motion. Now, because the motion, only a percentage of the torque goes in here. And because of the motion, there is a back EMF now, which was not there initially. When the motor was not running, there's no back EMF. Now it is running at some speed, there's back EMF. Therefore, this current also reduces. Now you can't draw as big current as you get initially because of the back EMF reduces the actual voltage applied on the motor to drive a current. So all in all, this is going to saturate at some point, and after that there won't be any acceleration, and the entire whatever torque generated will be used to maintain the speed. Okay, so it's very important to know how a motor works, right? Basic motor equations. Now what you do is you write this equation, the third one, torque is replaced by this one, K tau IT equals this part. You combine these two equations, right? And now it is current and angle relationship. Current and angle relationship. Okay. Now when you put it into Laplace, this becomes Is. K tau go to the right hand side, 1 over K tau. J equivalent theta double dot M. So that becomes S square theta ms once you neglect the initial conditions. Plus B equivalent theta dot M becomes S theta ms. All right. So then that is the equation 1 over K tau J equivalent S, right, plus B equivalent times S theta M. You get S theta M out of the bracket. Now this equation 3.7 can be used to replace current Is in the previous equation. That is this one, 3.69. This current was not needed. Now we can replace this current with this equation and we bring in additional terms, right, theta M. So theta M, that's fine because theta M and theta are related very beautifully, right? So that we can convert the equation which is in theta M into theta very easily. So this is exactly what we do. We has put 70 into 369. So then 369, this Is is replaced. See, watch out here, R plus Ls, then after that Is. So Is is this part. So it becomes like this, R plus Ls, this is Is, 1 over K tau, plus KBS theta ms. So you get this equation. Now you do a simplification, right? K tau goes left-hand side, K tau Vs. You get this one and theta over V, right? This is theta M over V, Vs is equal to K tau over this one, right? Now you see this is an equation between theta M and V, theta M and V. That is the motor angle versus the voltage. But if you really want the load angle, the angle of the arm, it is this, theta over Vs. Then the right hand side will be divided by N, the gear ratio. Okay. When the motor turns N number of turns, the load goes by 1 turn, right? So you get this equation. So this is what's called the system transfer function, 373. So let's do a MATLAB simulation. We have the series inductance, L, resistance, gear ratio. Our motor has torque constant and back EMF constant, and the equivalent inertia together with the motor and the shaft, this much, equivalent friction or damping is this much. And from the model equation, we have B2, B1, B0, A0. So these are basically these ones, the coefficients. There are 3 coefficients right here, Lj equivalent, and these 2 and this one. So we write Lj equivalent, this one, and what at the top is K tau over N, that is A0 here, right? K tau over N. So in MATLAB, this is how we declare our transfer function, because the transfer function command is there. You use TF and within bracket the numerator polynomial over denominator polynomial, right? So numerator polynomial is just A0, that is this one, numerator polynomial. You only write the coefficients of the polynomial. And the denominator has this one, this whole thing, plus 0. Okay, plus 0. Because this is the s term, s square term, s to the 3 term. So s to the 0 term is missing here. So therefore, when you write it as a polynomial, you have to write 0, this one, and this one. Like this, 0 and the other coefficients. If you have gone through a brief MATLAB exercise, you should have encountered these basic commands, transfer function. If you have a transfer function that you want to simulate in MATLAB, you have to declare the transfer function like this. After that, if you want to simulate the transfer function for a particular input, you have to say like this. This is step system, which means please run the simulation for the system with a step signal. That is 1 volt input, right? And simulate the response. That is what you are saying to MATLAB. So when you do that, this is what you get. This is theta, joint position. This is time, and it goes like this. You start with 0, and this is radians. It goes like that. The position keeps on increasing. Position of the motor, the load, right? That is the robot arm. The angle increases like this. Now, the transfer function you have is theta over V. Robot arm position versus voltage, right? If you want to look at the speed, how the speed of the robot arm is changing with time, what can you do? How can you derive that using the position transfer function? Can somebody turn on the mic and answer the question? How am I going to generate motor speed versus the voltage from what I have here, that is motor position versus voltage? Can somebody tell me? So I'm going to ask from someone.
Multiply by S.
Multiply by
S
S.
into S.
Yeah. So when you multiply a transfer function by S, what are you actually doing?
Getting d over dt.
You differentiate.
Yes, yes.
Yeah, that's right. That's the answer. You have to differentiate this with respect to time, right? But in Laplace domain, it is multiplied by S. And if you look at this denominator, there is S already. This S square, S to the 3. Get one of these S's to the left-hand side. Then it will go to theta S. Like this. So your transfer function is now going to change. 3.73. It is the robot arm speed versus input voltage. So you can have your MATLAB code modified, right? like this, P system, this is position, right? Like this. This is the transfer function. And if you look at V system, which is velocity transfer function, right? It will change like this. Earlier, if you look at this denominator polynomial, it has 4 components, right? S to the 0, S to the 1, S to the 2, S to the 3, 4 components. Now the velocity transfer function, you have only 3 components, S to the 0, S to the 1, and S to the 2. And you simulate using subplot command now because you want to have 2 graphs on the same screen. So you need to partition the screen into single column, 2 rows, right? So this is 2, 1, 1, 2 rows, 1 column, and you go for the top one, right? 1. And draw P system, position, right? Profile. And the subplot 2, 1, 2, that is 2 rows, 1 column. Second one, that is the one below, you have the step response V system for a certain duration, velocity system. And this is what you see. The position continuously increasing, velocity start with 0 and ramp up, and after some time the curve is actually flattened gradually and it becomes perfectly flat somewhere here, right? And it settled down at this particular speed. So after that, it will turn continuously with that speed. Clear? So now your initial answers to my question, what would you expect? Right? This is not going like a stepper motor or whatever. The second answer somebody gave me is correct. It will start running at the same speed, right? That it achieves at some point of time, and it will run forever. Can you tell me what is the most common apparatus to this exercise that we use in our houses and a lot of places? What is that device?
Ceiling fan.
Ceiling fan, pedestal, table, ceiling. The fan, yes. So you turn it on. It's running at a constant speed. And let's say it's too hot. What you do? Your fan is running, but still it's not, it's hot. Then what you do?
We have to put the oil or something.
No, the other way around. Now every fan has different stops, right? 0 is off, then you have speed 1, speed 2, speed 3, speed 4, like that. What you do is you turn the knob to step 1 to 2 to 3. As it gets more hotter, right, during the day, 1:32, right now it's too hot, right? I'm running my fan, maybe you can hear the sound, still at 1, right? But if it gets a little bit hotter, I have to put it to step 2. So then what I do is I provide there's a multi-tap transformer in these fans, right? If you go to the basics, a multi-tap transformer, and then you can connect the voltage from different taps, maybe 100 volts, 120, 130, like that, small volts, right? To up to maybe 230, right? Then you get the same voltage. And there are all other voltages also. So when you connect different supply voltages, right, here you can see this voltage. This is coming from say a multi-tap transformer, right? So this is DC, but if you look at the other side, AC to DC conversion and all, if you increase this voltage here, this voltage will also increase. Okay, so if you're running DC motor, it's like this, but fans are not DC motors, so then you can directly connect, right? So those are all electrical stuff. When I increase this voltage, right, directly, or after going through the say inverter converter process or multi-tap, whatever it is, right, you are changing this voltage to get higher speed, to get to higher speed, right? So then you are running over here, but when I change the tap to position 2 to 3, it goes again like that and go to a higher speed, settle somewhere here. So this is very nice exercise for you, right? Do it yourself. Do it yourself, right? You model it yourself and do the MATLAB coding yourself and see the graphs on screen. Okay. So then change the voltage to different volts. Then you can see this is changing the speed of the fan. Right. Any questions up to that point? This is a very nice example, very educational. When you go through the entire example, right, you learn quite a lot. Not only the mathematical thing, right? You first look at the apparatus you have here, physical system, the electrical system, mechanical system, and then write down the equations, that is modeling, right? And then you do this simple coding in MATLAB and you simulate and you verify your result. So that is why it is so elegant. Any questions? Now still we don't have controls, right? Remember, these are all analyzing the systems, right? And developing the relationships and coding and verification, that kind of thing. Still, we have not tried to control anything in particular, right? The way we desire. But this is the core. This is the core. To know how the systems work, how this electromagnetic system, electromechanical system works, right? When you put a voltage, you get the constant speed on the other side. So now if you want to change the speed, right, you know what to do. You change the input voltage, right? So then you can have some sort of combination, some communication from motor speed to the input voltage. And that is where things get more interesting. That is where controls start actually, right? Take this output signal, that is the speed of the arm, and then feed it back to the voltage to adjust the voltage, right? So that's going to be the controls, right? Now, before that, I want to show this to you. Now, let's say you have a plant, and if you know what is inside, just like this example, electromechanical system, you can write down the equations and derive the transfer function. Fine. But if you don't have this internal view of the components, how they're connected and so on and so forth, right? There's an experimental way to determine the transfer function. That is this. The basic equation is Ys over GSRS. Is that right? So go back to the transfer function. Say something like this, theta S over Vs. This is the transfer function. So we call this GS. right? Theta s is equal to Vs times Gs. This whole thing is Gs, transfer function. So if I replace this whole thing with the symbol Gs, right, I get this one. Ys is the response over Rs is the reference or input. So output over input is equal to Gs. So Gs is a rational polynomial of S. Now, if you start from there, and if you further say that your RT, that is the input to the plant, right, is delta T. Is delta T. What is delta T? Delta T is an impulse. Delta T is an impulse, like, for example, delta T is like this. This is time 0. Just that. At time 0, there is a pulse, RT. For that one, RS, Laplace transform is 1. So that is there in the table. Look at the Laplace table. Delta T, time function, Laplace transform is 1. So this is the situation we are in. We have the plant. We don't know what's inside. We don't have an equation, transfer function. What you do is you give an input, delta T, to the plant. And when you input delta T to the plant, an impulse to the plant, you get a response, right? You get a response. If you observe using an oscilloscope or something, you can see the waveform, the response. It's like you bang on a bell, right? When you do that, you see the ringing coming as the response, something like that. You give the impulse input and then record the response. Now, the response is Ys given Rs equals 1. When Rs equals 1, on the right hand side, it is only Gs. So very simple. Give the plant a delta or impulse and observe the output. And output is Gs. In Laplace domain, Gs. In time domain, Gt, this one. So you record the response, that is Gt, and find out the transfer function, Gs, right? And that is the transfer function of the plant. So for unknown plants, you can do that. That's about that part of the lecture. Any questions about that? Questions, please. Okay, then let's take a little break about 10-15 minutes, right? And start the next section.
Hello, sir.
Oh, sorry, I kept my mic turned off quite a while. So what I was telling is that so far we have studied about the plant, and if you give an input to the plant, right, it generates an output. So we simulated it in MATLAB and got the curves, graphs, and verified, right? So that itself is a huge part of this whole thing. But we did not look at whether the response is what we want, right? Whether the response is what we want. But it was what the system gives out. And if you want to change the response the way we want, right, you can look back of what you did and figure out either we have to change the input or change the plant, the system. So when I say change the plant or the system, that is, I'm referring to the spring and the damper in the shock absorber, or I'm referring to the resistors and the capacitors in the RC circuit and the components in the plant. So of course, that is not going to be the case here, right? Therefore, the only way to change the output or the response the way we want is something to do with the input, right? So we want to now change the input until the response changes in a desirable way. That's what we are trying to do. So everything is very rational here, right? You see, we give it a reason before we do something. So therefore, I want to take the response, right, and measure it. And of course, I can put a gain here so that I can adjust it, right? And if it helps me to do my job, so good to have a gain. And then over here, right, I have this new part coming in, the summing point, where I have a reference input now. Reference input now. It is not the previous reference input, a new one, which is actually the desirable response. Desirable response, right, as the reference input here. And any difference between these two, right, will tell me, signal me that I have to do something to change the response. So I get the difference between these two and try to control the plant. This is not the unique way of doing this. This is one simple way, or simplest way rather, of trying to build some sort of control into a plant. Okay, so only the concept building we are doing here. So what if I get this difference between the global reference and the actual response, and if there's an error, I drive the plant in the desirable direction so that the response will change, so that successive feedback, this difference will diminish, and when the difference goes to 0, you achieve Ys equals Rs. Simple. So in control systems, you can do whatever you want to a plant, right, in order to achieve this Ys equals Rs. So you make the adjustments, you make the connections, you change the gains, right? You can do absolutely anything, right? And if it helps you going forward, right, to make YS equals RS. So that is the entire objective in developing control systems, right? And this is the simplest way of trying to build something like that. And this is not perfect, right? There are a lot of defects here, but this is something that you can get going, right? Now I want to change this block diagram, right, to this one to give you more insight into what's happening here. In order to get the response, YS feedback, right, you need to have a sensor. If it is a position, maybe you can use a motor encoder, right? If it is a temperature, thermostat. If it's a pressure kind of thing, you pressure meter, right? If it is speed, you can have a tachometer. Like that, there are different sensors, right? The sensor reads the response. And then it feed it back to the reference input through a gain. So why we have a gain? Let's see. If you have a gain rather than connecting directly, right, it will help you to do something, right? If you don't want a gain, you can just keep it there as 1, right? Fine. Now, when you say a sensor, right, how does the sensors work? How does sensor work? So this is typically the sensor response curve, right? So when you expose a sensor to an stimulus, right, the response of the sensor, this is the input of the to the sensor, this is the output of the sensor, right? It goes like that and settles somewhere here. It is also not instantaneous, right? It also takes time to build the response, to measure. Now, if you think a sensor to generate the response like this, it takes some time to actually give the reading accurately out of the sensor, right? And if you read the sensor before that, you get misled. So therefore, this is an issue. So you need to keep an eye on and whether the sensor is stable or not. If the reading is changing, you know that it is not correct, and you have to give time until it gets over here. When the value is settled down, only you read it. So this is additional overhead of using sensors. So therefore, the sensor developers take care of that, and they make sure the sensor development, design and building, they use proper techniques so that it gives you almost instantaneous response, right? Those are the sensors that we use in systems where we don't have time to wait, right? And we don't have don't need to check whether the sensor is settled down before we read. None of these things are good in control systems. So therefore, we assume that the sensors give instantaneous response so that there is no delay here, right? Under that assumption, we set HS equals 1. That is ideal sensor. Now, if you look at these mercury thermometers that you use to measure body temperature, they are not of this category. They are the different type of category because they are not going to be part of a control system feedback, right? Just to measure. So you can wait a couple of minutes to get the reading, right? So we are referring to feedback system. So therefore, temperature measurement or whatever other measurement has to be different, the sensors, and they should give instantaneous response. Okay, so you get rid of mercury expansion temperature reading. If you want to have any temperature reading in say a control system feedback loop, maybe you can think about the laser based temperature measurement and things like that. Okay, right. So whatever it is, finally the sensors are actually instantaneous responsive sensors. So HS equals 1. So it goes out. Now, can we write down the signal flow, right, like this, because this is a feedback loop, right? So I'm going to write Ys, the response Ys is equal to Rs minus K times, right, Ys, and then it goes through Gs is equal to Ys. This entire loop, right, this entire loop. Ys is equal to, right, R minus KYS times GS. Simple. So now you simplify this equation to get Ys over Rs. Ys over Rs. So then here you can see Ys over Rs is equal to Gs over 1 plus KGS. This is a very, very important equation, 4.1. The most common equation in control systems, right? And on the left-hand side, we give it a name GCS, which means the closed loop transfer function. The loop is now closed. It was open. Now with the feedback, it is a closed loop. So therefore, we don't say GS, but GCS. GCS. Now, when you look at this one, GCS, right? It is Ys over Rs. You can draw it like this. You can draw it like this, and it looks like open loop. There's no feedback. But if you look at inside, you understand what is going on, right? There are internal feedbacks, right? So then we get to this one. So when the signals are actually traveling inside like this, it looks like a complicated thing, right? Every iteration, Ys changes, right? Feedback changes, goes on. So it's a complicated thing in time domain. But in Laplace domain, it's simple as this, right? Simple as this. If you know the open loop transfer function, which is Gs, you put it into this equation, Gs over 1 plus Kgs, and that is your closed loop transfer function. And interestingly, the K, the feedback gain is over here, which means now K is going to affect the response, right? Better or worse, okay? So we're going to look at that, how we can leverage on K, right, in order to make things better. Right. Now, all right. Now, let's create a situation here from what we already know. So you can see the RC circuit we analyzed earlier, right? So it's very familiar to you. And this is the equation, right, of the plant. And A is R1 R2 plus over R1 R2C, and B is 1 over R1C. So you have done all these things, right? And then you write down the Laplace and get this one, Vs over Vs is equal to Bos plus A VSS. VSS is this one, supply voltage. Vs is the output. We have done this, right? We have done this. So when we bring this input, right, to the left hand side, you generate the transfer function of this circuit, that is B over S plus A, right? It's a rational polynomial of S, but it's very, very simple. And this is the denominator. And when you set it to 0, you get the pole. This is a single pole case, first order case. And S equals minus A is the position of the pole. Okay, right. So these things you have done already. You have done already. So now the new thing here is that I'm going to design a system around the circuit like this. I'm going to put a voltage sensor across the capacitor and feed that voltage signal through a gain into a summing point here. And I'm going to introduce a new request to the plant. I want the voltage to be at this level, whatever, right? Not what the system naturally gives out, but I want it to give me this signal, this level. And if there's any change between these two, you generate a difference and you use that one to drive this voltage. So now this one is not a constant. Now you're going to change it. You're going to change it, okay, based on this difference. Now all these signals are new now. These are new signals, right, designed around the core of the plant. This is the core circuit. Around that, now we are trying to manage the system, right? It's like there's an engineering stuff, and around that you are trying to do some sort of management, right? Arranging signals in a certain way. Then to see whether we can get this output to be equal to this input, right? This is the demand. Okay, I want it to be at that voltage, and whether we can get the actual voltage to that voltage. Now, based on what we learned earlier, the closed loop, if you close the loop like this with the feedback gain K, right, the closed loop transfer function, which is V over VR. It's not this one, V over Vs. V over Vs. That is the open loop. The closed loop function is V over VR. And that is actually coming from here, Gs over 1 plus Kgs, as we derived the equation earlier. Gs over 1 plus Kgs. So we write it like that. This is Gs, right? B over S plus A over 1 plus KBS. So when you simplify it, it becomes like this. It's also a single pole case, first order plant, but it is a different plant, right? So it's equals minus A plus KB is the pole. It was minus A earlier. Now with K, it's going to change. Clear? So if you draw the pole plane, right? If you draw the pole plane, say like this is real axis, this is imaginary axis, this is the pole plane, right? It was like minus A. It was like minus A earlier, right? For the open loop plant, this one. But now it is S plus S equals minus A plus KB. So now you can have a range of positions, right, for the poles, for the pole rather, right? Doesn't have to be here. You can move it this way or that way. Now, all of the cases we discussed up to now, the poles were on the negative half of the S-plane, right? Negative half. Remember the shock absorber? It has number of different types, right, of responses, oscillatory, whatever it is, they were all on the left-hand side. Because this pole goes to e to the, this pole times t, right? So it has to be minus to be stable. In the response, the exponential term e to the plus something means that the signal is growing indefinitely, right? So that is very unstable case. It happens when this minus a, right, this number which is negative, all these cases becomes positive. In that case, it is not exponential decay, but exponential rise. So system is unstable. Okay. Now this one might bring this pole to the right hand side. Right? If you pick up a negative gain, negative k, and it is big enough to make this whole thing positive, then you have a pole over here. Unstable case. So we'll look at that. So there are a few other things that we need to collect on the way. One thing is the DC gain, what is called the DC gain. For a plant, right, when you give a signal as the input, and if you want to actually find out what is the final value of the response, right? What is the final value of the response? Response can be oscillatory, can be non-oscillatory, whatever it is. If it ever settles at some level, right? The final value. What is that value? It is given by what is called the final value theorem. So make a note of today, study, self-study, final value theorem, and I give you the equation here. The final value is given by this one. In the book, there's a chapter, Laplace, there you can see the final value theorem with the proof. So the theory finally is this: limit as s goes to 0, s times gs fs, whatever input that you give to the plant, right? The final value is, this is the input a over s, because here it is, the input is a unit step, not actually unit step, it's a constant, right? Step size, it's a step signal. So a u s t. So when you write this down in Laplace domain, it becomes a 1 over s, a over s, this one, okay? And gs is the plant. If it is whatever plant, open loop, if it's open loop plant. If it is closed loop plant, it's closed loop plant, whatever it is, right? So take that one, gs or gcs, as appropriate. And in front of that, there's an s. That's it. So that is the final value. Final value is something that is in the time domain, not in the Laplace domain. But to calculate that, you can use the Laplace domain terms, gs, etc., and take the limit as s goes to 0. The result is not in the Laplace domain. Result is the value, the final value of the plant. Now, if you take the a over s part out, this part out, this is input, no? This is the input. right? If you take that part out, what is remaining is called DC gain. It's a gain as a percentage, as a fraction of the input. What is the fraction that goes from input to the output? That is what it says. Okay. So then that part alone is limit as s goes to 0 GS. So if it is open loop, you use GS. If it is closed loop plant, you use GCS. Whatever plant that you are referring to, you use. Okay. So if you look at the closed loop RC circuit we just derived, right? You can write the DC gain of the closed loop RC circuit like this as limit s goes to 0 GCS. So what is GCS? GCS is this one, B over S plus A plus KB. So as S goes to 0, this becomes B over A plus KB. This is the DC gain, B over A plus KB. So if you know B, if you know A, if you know K, you can calculate this as a fraction, 0 to 1, or maybe more than that, 0.9, 1.3, 1.5, right? Whatever it is. This is the portion. This is the portion of the step signal input that the value finally attains. So there also you can see K here, right? K is the feedback gain, and it is there in the feedback in the DC gain also, which means you can control the DC gain, right? You can control the DC gain by changing K. So we are going to exercise some degree of controls here through this K. By changing K appropriately, now we can exercise some controls on the plant. Now see, this is how we get control to our hand, partially or fully, right? You want to put a gain somewhere, right? And connect the loop around, right? Get the signals from one place to another and put the comparison in, right? Then you control your gain until you achieve the desired response. So that is the philosophy here, right? That is the plan here. So wherever possible, you put gains, 1 or 2 or many, right? In addition to that, you connect the sensor system, summing points, etc. And you gain some sort of control over the plant. So now, if you look at what will happen as you change K, we can immediately see now this is the pole of the plant. This is the DC gain of the plant, right? So if you increase K, right, this will reduce further. So DC gain drops as you increase K. And if you look at the pole, if you increase K, the pole is going to negative infinity gradually on the real axis. It is moving towards the negative infinity. So when you have poles located far from the origin into the negative infinity, you know it is fast poles, very quick response. However, the DC gain will be very, very small. So therefore, you don't see a significant response coming out of the plant. Even though whatever small response come quickly, right? Very fast response, but it's not big enough. So now we are going to do a bit more extensive analysis of what is happening if you change k, right? So, for example, the easiest one to start with is k equals 0. If there's no k, if it is 0, it's an open loop. It's an open loop. So therefore, when k is 0, right, the DC gain is B over A, and the pole is minus A. It is the open loop case. Then when k is negative, what will happen? This is the pole. When k is negative, this whole thing goes less than A, but it is still negative, less than A, negative. So which means the pole is moving, right? Let me take the pen. This is our plane. This is minus A. Right? Now, if you increase, if you reduce k less than 0, you are moving gradually towards this direction. Okay? K less than 0. K greater than 0, you are moving that way. So this is something that you need to keep an eye on, right? So if you move that way, k is positive, and if you move that way, k is negative. Okay, so this is an interesting situation. Now, if we set R1 and R2 are equal for the circuit, A is this one, R1, R2, R1 plus R2 other over R1, R2C, it becomes 2 over RC. Then B can be written as 1 over RC. And further, if you say k equals minus 2, now set it to minus 2. K equals minus 2. So it should be somewhere over here, right? To the left, to the right of this point. K equals minus 2. So then we can write our transfer function y is, right? Remember our transfer function? So this is our transfer function b over s plus a plus kb, rs and ys, right? So b over s plus a minus 2b now, right? Because k is minus 2. So you replace k over here with minus 2. So why I use minus 2? It's because then this becomes 1 over RC, this becomes just S. So when the gain is minus 2, you attain a very interesting situation in your feedback system. That is 1 over RC, 1 over S, RS. So this is the response, YS, for an input, RS. So what does it say? 1 over S, RS means, as you know, 1 over S comes when what happens in time domain, would you get 1 over S, RS? Does anybody remember that? When you see 1 over SRS, what is it in time domain?
Impulse?
No, this is 1 over SRS. 1 over SRS is not just 1 over S. 1 over S means a step signal. but 1 over s rs. There's a input signal rs, and in front of that there is 1 over s. So if you want to do inverse Laplace of that one, what is it in time domain?
Integration.
Integration. If you look at the Laplace table, it is integration of RT. Integration of RT. 1 over s means integration in time domain of what? The time function of this one. The time function of rs is RT. Like this, you integrate it. And 1 over RC is over here. So this is a plan which is an integrator, basically. If you give an input, it will integrate the input and produce a response. It may not be what you want, right? But this is basically an exercise for us to figure out, if we play with this gain k, what are the possible outcomes, okay? So there's a name given to this kind of responses in plants. It is called rigid body dynamics. It's called rigid body dynamics. So everything is actually accumulated and produced as an output. It's just like a rigid body, okay? But plants are not generally like that. Whatever you give, it does not immediately accumulate and respond. It goes through a certain dynamic pattern and before producing the response, right? It's almost like you throw a piece of rock. There's no spring action, there's no damping, there's nothing, right? It just behaves like a piece of rock, rigid body. And you can achieve that one when k is exactly -2. When k is exactly -2. So can you figure out where the pole is then? When k equals -2. Where's the pole?
To be minus a.
2b?
Origin.
To
It
be
has the
minus
origin,
a.
sir.
So there's one answer saying that 2b minus a. So what is 2b minus a? You have a and b here.
0.
The origin.
0. Yeah, somebody said origin. So this is highly enlightening now. So now it is, the pole is not here, pole is at 0. So this is the pole, right? Oops. The pole was here. Now it is over here. Now pole is over here. Right? When k equals -2. This is very interesting. So whenever the pole goes to 0, the origin, you have rigid body dynamics. And here also you can see, it is 1 over SRS. So denominator is just S, which means the pole at 0, S is equal to 0, right? Rigid body dynamics. Then if you further reduce, when k is less than -2, the pole is positive, right? Of course, you know. Now, when k is, this is k less than -2. So this whole area is like that. K less than -2. So this is exactly k equals -2, right? This one. this is the last stop where system can be maintained in a stable fashion, even though the rigid body is also not good, right? Beyond that is worse, which means pole is positive. Now you can have negative poles, you are happy, there is no stability issue. Pole is 0, you have some concerns, right? And pole on the right hand side positive, you have serious problems. The system is unstable. Now, because this is a single pole case, this is the response, right? You can simply solve the differential equation and get this response. So you can solve Laplace and get this response, yt, right? The response, b over a plus kb, 1 minus e to the minus a plus kbt, right? So you know when the k is less than -2 here, right? This e to the function, right? It becomes positive. So then you are in big trouble. So now what are the other interesting points? Let's look at the value of k, which results in unity DC gain. Okay, right. If you want to have unity DC gain, I think this is one of the priorities, objectives, to have unity DC gain, which means input is equal to the response. Okay, you get the same level at the output, right? The response as of the input. So you write the equation for DC gain, that is b over a plus kb, set it to 1 and calculate k. So k will be -1. Of course, this is when R1 and R2 are equal. So -1 is somewhere here. Somewhere here, right? So somewhere here, k equals -1. Somewhere here. Right? So you have a unity DC gain when the pole is somewhere here. So all these are different scenarios as you change k. So let's do this MATLAB simulation, right? So up here, we have the resistor 1 kilo ohm, R1 is equal to R2 here. And we have the capacitor, this is A, this is B. And I'm simulating the system for about 600 milliseconds. I'm drawing the output voltage and control voltage. So there are two things here, output voltage and control voltage. So this is the output voltage, this is the control voltage, okay? Right. And I have gains, right? Feedback gain K, here it is G, right? G is 0, and this is AG. When you do the open loop, it is going to change, okay? This is the circuit transfer function BO1 and AG, right? It's a single first order case. And I have different gains, -1.5, 2, -2, 2.5, minus, like that, different values, right? Because we know the interesting values are like k equals 0, open loop plant, and k equals -2, rigid body dynamics, -1, unity DC gain, and when it is below -2, it's unstable. So we just want to pick up some numerical values in those areas and put over here for G. And the control voltage is Vs. Control voltage is Vs. So how do we calculate control voltage? This one. This is the control voltage, right? So if you want to monitor the control voltage, you have to make the control voltage the response. So for that, you need to have additional transfer function, not the one we have already, which is V over VR. Now you need to generate Vs over VR. Vs over VR. So how to do that? How to do that? If you want to get the control voltage, right? Not the output voltage. You want to get Vs. So you have to twist the whole thing so that this G comes to the feedback path and this guy Vs appear as the output. This is for the sake of developing the transfer function. Okay. So I give this as an example for you to do, right? I haven't included in the lecture, in the slide rather. So can you do that? Can you find out, right? Because you know this part, GS, right? Take GS into the feedback loop and take Vs as the output, right? And derive the closed loop transfer function. And then you can have Vs as the output. But if you follow the chapter in the book, it is there. So we are monitoring both these voltages, the output, that is the voltage across the capacitor, as well as the voltage which is driving the circuit, okay, which is driving the circuit. That is control voltage. And this is the result. Output voltage over here, and you can see the control voltage over here. So for various values of K equals 0. It's like this. K equals -1. -1.5. Right? Then -2. Rigid body dynamics. You can see this linear curve, accumulation of a step signal, right? See, when you accumulate step signal, you get the linear curve. And when K drops below 2, it is increasing, exponentially increasing. That's not good. Output voltage, you can see K equals 2, 0, -1, -1.5, like that. So it makes a good sense. And if you look at the DC gain, unity, which is actually set by setting K equals to -1, I guess, right here, -1. So then you can see the output voltage goes like that and finally settle over here, and the level is 1. Yes. So because what we are doing is the step, unit step response. So input is 1. So the output is 1 as well, right? So when DC gain is 1. So when you clamp the system to have unity DC gain, this is what happens. Output is equal to input in the long run. So when that happens, you can see the supply voltage, control voltage rather, when K equals -1, settle over here. So it needs to have 2 volts. Needs to have 2 volts because you know this is a potential divided circuit. When the system settle down, so if you want to have 1 volt at the output, you need to have 2 volts at the supply side. Right. So now you can see what we learn here is that there is a range of controls. There's a range of controls, right? With even a very simple circuit, feedback loop like this, right? Feedback loop like this, right? This is not a very mature feedback control system, right? But it also gives you a fair amount of controls, right, around this circuit. Right. Now I'm going to give you a design example, right? Please do that. And how can I get this? I really want to do this an exam exercise, but anyway, because the thing is, it's not easy to do any assessment here. So therefore, we'll do this as a class exercise, right? I want you to do this. Design the RC circuit feedback gain for 50 millisecond time constant. I want you to design the plant, the same plant we have been dealing with, to have 50 millisecond time constant, right? And unity DC gain. That's the second part. I'll come back to that maybe later. First, can you do this one? So R1 and R2 are 1 kilo ohm each, and the capacity is 200 microfarad. Please design the circuit to have 50 millisecond time constant. Can you do that? So take about 5 minutes, right? And prepare your answers.
Excuse me, sir, the mic is off.
So this is the closed loop plant, and this is 1OS, right? This is straight away coming from the closed loop transfer function where Ys over Rs, right, is the transfer function. And now we take this Rs from here and put it over here, 1OS, which is unit step, right? And we can solve this one, B over, right, A plus KB, 1 over S minus 1 over S plus A plus KB. It's very straightforward, right? Don't have to go through Laplace in the sense all these procedures, right? In fact, it is Laplace. We know 1 over S is 1 over S plus this one is e to the minus A plus KBT. So pretty straightforward thing, and we have done that earlier. Now the time constant discussion comes over here. Now you can see this A plus KB times T, and this is the time constant. In fact, the time constant is 1 over this one, the exponent right, is a reciprocal of time constant. So therefore, for this response, the time constant tau is 1 over A plus KB, this one. Then you can calculate K out of this as 1 over B, 1 over tau minus A. So which means A and B are system components, right? Resistors, caps, etc. And tau is whatever you want. Let it be 50 milliseconds or 100 milliseconds, whatever it is, you put it that there and then calculate K. So which K gives you, right, 50 millisecond time constant. So if you want to have 50 millisecond, right, when A and B are already given like this, 2 over RC, 1 over RC, right, this becomes 10, this becomes 5 because R and C are given, right? See, R is 1 kilo ohm, C is 200 microfarad. So with that, gain for 50 milliseconds, right, 1 over B, right, 1 over tau minus A. So this is 1 over tau, right, minus A, whole thing divided by 5. That is about 2. K equals 2. Okay, so K equals 2. So if we go back, K equals 2, right? This is K equals 0. This is when K greater than 0. So maybe somewhere over here. Right? Maybe somewhere over here. What is it? K equals 2. Right? And you have 50 millisecond time constant when the pole is over here, right? And that time K equals 2 and the time constant is 50 milliseconds. Now we move on the same exercise, right? If you look at the previous one, it has 2 parts, right? First part is to adjust the DC, adjust the 50 millisecond time constant, and second part unity DC gain. That is the second part. Now with the 50 millisecond time constant has already been achieved. Now we can follow on, right? And take on the other one, that is unity DC gain. So how are we going to achieve that? Can somebody suggest a method? Propose a method to improve the response to have same magnitude as the input, that is unity DC gain. How are we going to adjust the DC gain to make it unity, right? Any ideas? Any suggestions?
By adjusting K, sir?
Say it again.
By adjusting K?
Really? You have already adjusted K to get 50 millisecond time constant. Now, if you adjust it further, maybe you can try getting DC gain, but you will not be able to achieve 50 millisecond time constant. So now you can't adjust K anymore because you have already used it and set it to have 50 millisecond time constant. I think this discussion is interesting, right? We want to develop this rationale for whatever we do, right? Why we do it, to achieve what, and then can we use it again to achieve something else, then what happens to the previous one. So it's not logical to again try to adjust K. Keep thinking, yeah. So any other answers? So I think for a lot of things, right? You want to solve problems. Maybe you can't have a solution in a flash. Okay, solutions are coming at the end of the process, that you need to understand. Therefore, that is why you need to engage and get the process going for everything without actually trying to get the question, the answer up front. Answer stays at the end of the process. So all what we need to do as engineers or any other professional, right, to understand the problem first and give it a rationale and get it going, and on the way you will find the solution. Okay, so try to learn it that way. It takes a little time, but eventually you will be able to find the solution. So keep it as a lesson, right? That will help you solve many problems. So what I do is, why I first calculate, okay, what is the gain now? Then after setting k equals 2, right? What is the DC gain? You just calculate it. DC gain is equal to B over A plus KB. I had the equation earlier. That is 0.25. So now I have 50 millisecond time constant and also 25% DC gain, right? So what I do is, I know I have no other degrees of freedom on the system. I have actually no leverage on any of these things. I have exploited whatever available, exhausted, right? So now what I can do is to get the reciprocal of this, that is 1 over 2.25, and put it as a gain. So this new gain which comes over here is 1 over DC gain. So this whole thing over here, right, 25%, 25%, or 1/4. And here you invert it 4 times. You put a gain, 4 times gain here, 4x, right? Then what comes over here will be as same as RS. That's very simple. So sometimes you have to draw, sometimes you have to sketch. Certain things, then it will help you to explore a solution, right? So engage with the process. Keep thinking will not sometimes help. Draw, write, right? Do whatever to get the process going, and all of a sudden you will find the solution, right? So in this particular case, DC gain is 25%. So you need to have a forward gain 1 over 25, that is 4. You are done. Then you achieve time constant 50 milliseconds as well as unity DC gain, both. Now, as everything we did up to now, we need to code it and see whether we get what we want. So again, this is part of the MATLAB code. You have resistance, capacitance, A, B, system components, simulation duration 600 milliseconds, and you have subplot 211, 212 to draw the control voltage, output voltage for the new values, right? So gain is 2 now. Gain is 2 now, and now our transfer function is 4 times the earlier one, because we have already calculated that we need to have 4 times gain, right? To get the DC gain to 1. So this is the result. You can see the output voltage, it goes like that and settle over here, and it is exactly 1. The input is 1, output is also 1, the long hole, right? That is why it is called unity DC gain. And when you do that, the control voltage starts with 4 volts and gradually settle at 2 volts. So I think we have done. We designed the system to satisfy the requirements, time constant and DC gain. Any questions? Okay. Now, let's move on with the other system. So now you have got some experience about closing the loop feedback through a gain, and by adjusting the gain, you can have different types of responses and adjusting the DC gain, etc. Right? Gradually, we are getting control to our hand. Now, what about this system, the shock absorber? Right? Now, earlier it was just a shock absorber. When you jump onto the seat, it stabilize and settle down. That's it. Now I want to make the same mechanism. I don't call it a stabilizer anymore, or shock absorber anymore, but I give it a name, stabilized platform. Stabilized platform. So which means it's a very precision device. So when I said, okay, I want the table to be elevated by say 0.2 millimeter. I want the table to be lowered by 0.25 millimeters, something like that. So I want to have this mechanism to move it up and down and settle it at that point. Now I am introducing a signal, new signal to the plant. What is my reference height? What is my reference height? And when I give that, the internal structure, right, should apply force on the mass or reduce the force on the mass so that it goes and settle at that point. Okay, and I don't want to have rigid body dynamics. That's why I use the spring and damper. So whatever it happens, right, it happens in a gentle way rather than being a rigid body, right? So so the system here within the dashed rectangle is actually the existing system. The system we worked last couple of weeks, mass, spring, and damper. If there's a force, this goes down and settle. So it is not a feedback system. It is open loop. Now I put a level sensor here, right? Level sensor here, right? Precisely give me the position of the mass, and I send it through a gain, right? And this is the summing point, and this is my reference, RT. So I'm going to change RT, right? 2.5 millimeter, 0.25 millimeter, minus 1 millimeter, whatever it is, right? I'm going to give this value to RT. Once I give it a value, I want the system to gradually attain that and settle there. Okay. So maybe after a few oscillations or without oscillation, whatever it is, it doesn't matter. We can design the loop accordingly, right? So all of a sudden, this open loop shock absorber becomes a stabilized platform. Now see how this basic shock absorber, right, is fitted with additional sensors, feedback loops, summing points, and a reference point, and how we can make it as a stabilized platform. Okay, so this is designing the control system around an existing plant or device. So the open loop plant GS is already known, eta over S square plus 2 sigma S plus rho. This is what we have already derived. And we have already derived the closed loop transfer function also. If you have open loop transfer function like this shock absorber here, and if you generate a feedback through a gain, right, like that, through a summing point here, and then you get the difference as a control signal to drive the force, right, onto the mass. Okay, so we design this loop here, signal connectivity, right, gain, etc., to make it a feedback closed loop plant. So when you do that, the closed loop transfer function is given by GS over 1 plus K GS. Don't forget that. It is the most common equation in control systems. The feedback closed loop transfer function. So now we write that one, GCS, as the GS over 1 plus K GS. So when you simplify, it will look like this, eta over S square plus 2 sigma S plus rho plus K eta. So it is slightly different from the open loop transfer function. Now it's like this. Okay. Now, where are the poles of the new control system, right? Closed loop transfer function. So you set the denominator to 0, and your poles are minus sigma plus or minus square root 2 sigma square minus rho minus K eta. So these are the solutions. If you look at this quadratic equation, right, with a pair of conjugate poles, it will be like this. Okay. So if you look at the determinant, right, if it is equal to sigma, so then you have one pole located at the origin. Remember, this is one of the things we want to avoid. Pole at the origin, right? Pole at the origin. Other pole is somewhere, but that's okay. The pole at the origin will get you what is called rigid body dynamics. Rigid body dynamics. And after that, that pole will enter to the positive half plane, positive side of the pole, then system is unstable. So therefore, we call whatever gain K that will bring one of these poles to the origin as ultimate gain, Ku, right? Or it's going to be unstable after that point. And there you can calculate it using this equation. It is eta rho over eta negative. And also you can see when the determinant is 0, we saw that earlier, when the determinant is 0, the two poles are on top of each other. Here, when this is 0, S1 and S2 are at minus sigma, coincident poles. So when the poles are coincident, we call it critically damped response. Critically damped response. So when you set this to 0, you can calculate your K, which is sigma square minus rho over eta, critical gain. So what I'm telling you is that you don't have to remember these equations, right? But remember the process, right? When you have the closed loop transfer function, get the characteristic equation and set it to 0 and get the solutions. And looking at the solution, you can set your gain in order to meet certain conditions like rigid body dynamics, critical damp condition, etc., right? So you can calculate, if you know eta and rho, right, and sigma, you can calculate what is the ultimate gain, what is the critical gain. So when K is less than ultimate gain, closed loop system is unstable. So when you reduce K, you also saw this earlier, when you reduce K, system becomes unstable. It goes to unstable area because when you reduce K, it goes from whatever positive value to 0 and then to the negative side. So when gain is negative, it is not actually feed negative feedback, it does positive feedback, right? So it doesn't serve the purpose. Now here you can see in the feedback, we need to have plus and minus, no? Plus and minus. Now all of a sudden, if you make K negative, what will happen? This negative becomes positive. So rather than getting the difference between the two signals, now you are getting addition. That is not the purpose, no? So therefore, it is fundamentally incorrect to have negative gains in the feedback. But having said that, I want to tell you there are very advanced control systems where this gain is negative. But that is entirely a different discussion for another day, right? And they don't keep the negative gain for indefinitely. It is only temporarily, and they switch back and forth, positive, negative gains. So they are very advanced control systems, right? So that we are not going to discuss here. This is for basically the relatively slow industrial processes, right? But if you look at, say, very fast systems like missile controls, for example, right? So there you have very different types of controls like variable structure, sliding mode, and things like that. So there you can see these feedback gains are changing the signs, plus, minus, depending on the state of operation. So that is a different thing. Don't worry about that. For our discussion, this level, gain has to be negative, okay? Sorry, the whole thing has to be negative here. So to do that, the gain has to be positive. So when you reduce the gain for our understanding, there are limits, right? Ultimate gain when K is like this, and critical gain when gain is like that. When the gain is less than the critical gain, ultimate gain, one of the poles is on the right half plane, that is unstable. Between these two gains, ultimate and critical, right? Ultimate and critical, the poles are on the real axis and they are different, distinct poles. So you have distinct real poles, so that the system is overdamped, and we know that, right? When K equals critical damped gain Kc, two poles on top of each other, control system is critically damped. And if you further increase K beyond the critically damped gain, the system is assumed to have pair of complex conjugate poles, right? So the whole thing is described over here, right? When the feedback gain is 0, system is open loop, and you have this and this, two poles. If you reduce K to negative, this pole goes this way, this pole goes that way, right? So this pole reach the origin over here when K equals Ku ultimate K, and after that you are unstable. And if you increase K, then these two poles go like they move head on, right? K between 0 and Kc, right? That is this point. They have two distinct poles, and when it is Kc, they are here. And if you further increase the gain, one pole goes up, the other one goes down. And then you have the imaginary component in the poles. It is a pair of conjugate poles. So the bottom line is that you can use this K to exercise any of these possible responses. You can make the system unstable. You can make the system rigid body. You can make the system critically damped. You can make the system overdamped or underdamped, right? You can do anything you want to the plant, right? If you design it like that by changing K, right? Okay, so I want to stop there for today, because time is almost, yes, 4:30. All right. Any questions up to now? Right. In that case, we will wind up for today, right? Thank you very much. I'll see you next week.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.